Hello everyone and welcome back. We are now looking at question 3 on our 2016 Galois contest. In the diagram, the triangle ABC is equilateral, so all these sides are the same, with side length of 6. And D is the midpoint of BC, and just like all isosceles triangles, which technically equilateral triangles are, A to D, this midpoint, gives us a nice height, a nice perpendicular altitude. We are being asked to determine the exact value of h, the height of our triangle. Okay. Well, it's a grade 10 contest. We can use trigonometry if we want to. We can, get a 60-degree angle here, and then use some trigonometry. Or, we don't have to do that because this type of triangle that we're going to use is actually fairly common. You don't need to bust out the sines and cosines. Okay, so if we just look at ADB as a triangle, what are the angles inside that triangle? Well, you'll get a right angle at D, and you'll get 60 degrees, because all these internal angles are the same. Okay, and they have to add up to 180. So you get 60 degrees, and that leaves 30 degrees here. We have what is called a 30, 60, 90 triangle. And 30, 60, 90 triangles come up a fair bit in contests, so it's good to know the ratio of the various sides. So if the side length opposite the smallest angle, the 30, is 1, then the side length opposite the 60, in this case our height, is going to be root 3, and the side length on the hypotenuse, so opposite the bigger one, the 90, is 2. Now, for our particular question, what do we want? We want the height here, and we know the hypotenuse is 6. So, the hypotenuse is to h as 2 is to root 3, or we can say that with similar triangle words, and not similar to, with similar triangle ratios. H to 6 is root 3 to 2, and then we can cross multiply, and we see that h is going to be 3 root 3 when all is said and canceled. Okay. You don't have to do that. Of course, you could put. They do tell us that D is the midpoint down here. So you could say, well, the midpoint of 6 is 3, and then 3 times root 3 gives you 3 root 3 as well. But there we go. And it's just a light bulb, so we do just need that final answer, but we have shown some work and explained what was going on. Okay. B part. In the diagram, a circle with center O has radius 6. Okay, not unlike the 6 we saw before. Regular hexagon, EFGHIJ, has side lengths of 6. And so we're going to get a whole bunch of equilateral triangles. One of the nice things about regular hexagons is you can always sort of cut them up like this. And so the side lengths are 6, and the vertices are on the circle, whose center is O. Determine the exact area of the shaded region. So the shaded region is what's left inside the circle, but still outside the hexagon. Okay, so the shaded area is the full circle's area, circle of radius 6. And how do you find the area of a circle? Pi r squared, so pi times the radius squared, minus the area of the hexagon. And they've already gone through the trouble to show us that the hexagon can be cut up into these smaller equilateral triangles of side length 6. So this is a nice common thing with regular hexagons. So how many of them are there? There's 6 triangles. So we want to do 36 pi minus 6 times this equilateral triangle whose side lengths are 6. But hold on. In A, we were able to figure out the height of one of these triangles. So we can say 36 pi minus 6 triangles, and each triangle is 1/2 a base of 6 times the height of 3 root 3. We could even mention this is from part A. And there we go. And so I've got, let's see, 36 pi minus 36 over 2 should be 18 times 3 root 3. So 36 pi was, yeah, it is 18. Okay, 6 times 6 over 2. 18 times 3 is 54. So we'll say 54 root 3. And that's our final answer. And that's all we need to put. Okay. So there we go. Circle area, breaking the hexagon down, and then triangle areas. And we used our height from part A. Although, if we wanted to, we could have recreated that height. Or we could have also used a formula for the area of an equilateral triangle, if you know that. So if you just know the side length of an equilateral triangle, the area is root 3 over 4 side length squared. So you could have used that, and you didn't have to use the height from part A. Well, that's okay. Either way, we've got our answer, and it is the exact answer. We didn't grab our calculator or approximate it. They weren't asking for that. Okay? If you want to, I mean, I'm just going to quickly grab my calculator just to have a good idea as to what the area is. It's about 19.5. The only reason I really did that double check with the calculator is just to make sure that it was a positive area. Okay. All right, now we've got C part left to go here. A circle has center O and radius R. Ooh, I don't know what R is. That's okay. A second circle has center P and diameter MN. The circles intersect at M and N. If MN is equal to R, determine the exact area of the shaded region in terms of R. This shaded region here, I believe it's technically something called a lune. I'm not entirely sure. You're welcome to look that up. But I think this is the geometric shape known as a lune. Not that it particularly helps calculate anything. Okay. What can we do? Well, we've got to figure out this area, and it's a very unusual area. So let's draw the picture for ourselves. Okay, M and N are on both, and M and N also happen to be the diameter of the smaller circle. Okay, so they are a diameter. If we cut it in half, so it's a semicircle minus, let's say, this blue area. So it's a semicircle of radius r by 2 for this smaller circle, because we're told that Mn is r. So the radius, not the diameter, okay, is r by 2. Okay, so what else can we do? Well, we also know M and N connect up to O. And we know that, I'll use some green here, OM, ON, these are length R because that's the radius, but MN is length R. So I've got a nice little equilateral triangle. So triangle OMN is equilateral. Okay? And that means that I'm going to get 60 degrees here. Now, I'll get 60 degrees everywhere else, but why do I care about the 60 degrees at the bottom there? Because if I look at, now I'll get out the red. In red, I've got this nice big sector of a circle. And I can figure out the area of a sector of a circle in terms of its radius and the angle of that sector. So I can figure out this sort of red shape and then subtract away the green equilateral triangle, and I'll be left with this blue shape, which I can then take away from the semicircle to get the shaded area. Okay. So, I would really recommend using colors for this. I'm going to say the shaded area is the pink semicircle minus the blue shape. Okay, and we can also see the blue shape is equal to the red sector of the circle minus the green equilateral triangle. Okay, So this gives me a plan. So my shaded area is the semicircle minus the sector minus the triangle. Now I know the radius for the semicircle. I already mentioned it over here. And a semicircle's area, well, a semicircle is just a sector of angle 180 degrees, but it's 1/2 pi r squared, which in this case is actually r over 2 squared. Pi times the radius squared, I guess. Alright, now the sector of a circle. In general, if I've got a circle sector, and it gives me an angle of theta from the center, and you've got a radius of r, you do theta over 360 degrees pi r squared. And it doesn't have to be over 360 degrees. It can be over 2 pi if you're measuring in radians. Doesn't really matter. But we're working in degrees. That's why I thought I'd mention it. So we get 60 degrees out of 360 degrees pi r squared. And the r doesn't need to change because r is the radius of the bigger circle. Alright. Minus the area of an equilateral triangle. If you are uncomfortable just quoting the formula that I actually managed to quote here, although I didn't use r, I used s, you're more than welcome to, as a side calculation, show people how to get to it. You know, we always get a 30, 60, 90 triangle, but in this case it'll be r over 2r and r root 3 over 2. Okay. And so your height, so your area here is 1/2 base of r times height r root 3 over 2, and that's where the root 3 over 4 r squared comes in. Okay, so you can show this to someone, although I would strongly suspect that if you just confidently said, this is the formula for the area of an equilateral triangle, you're not going to lose marks for it. Okay, and the side is still r. So we have a little bit of cleanup we can do. I can change this to pi r squared over 8. 1, 2 coming there, and then two 2's coming from the square. Minus 1/6 pi r squared. And then minus the triangle, so that would be root 3 r squared over 4. Now I can drop the brackets at the cost of changing this minus sign to a plus. We can take out a factor of r squared. And then we've got pi by 8 minus pi by 6 plus root 3 over 4. I suppose we could clean up and say it's 6 pi by 48 minus 8 pi by 48 and negative pi by 24. Okay, there we go. So that's not too bad an answer. I don't know if there's anything else I need to do. Determine the exact area of the shaded region in terms of r. No, I'd say we are done. Okay, we color-coded our picture to make it really easy to see how we were putting this stuff together. Semicircle minus the blue shape, and the blue shape is sector minus triangle. And then we get at everything in terms of r. So I'd say job well done. And we get ourselves ready for question number 4. We're going to finish off the Galois with question number 4, but we'll take a look at that in the next video.